Okay, so today I'm going to cover the topic of stochastic matrices. Before we start, I wanted to just clarify something, a question that was on the Piazza, and also, and the question is basically if you're going to compute, if you're going to write a matrix, say in the form x inverse dx, where x is some matrix which is the which contains the eigenvectors of A as the column vectors, then what does D look like? And the answer is D is a diagonal matrix which are really the eigenvalues of A. So in other words, if you take a matrix A, then its diagonalized matrix is nothing more than its eigenvalues written in this form over here. And one of the students, is it you? Are you Andrew Arnold? Okay, I got your name. Posted a very simple proof. His proof misses a few steps. I encourage you to try it out, but it is a correct proof. And so the diagonal matrix does, in fact, is nothing more than the eigenvalues of A written on the diagonal form. So you don't actually need to sit there and compute x inverse and all that. You can just find the eigenvalues of A from the characteristic equation and just plug in these values here in the diagonal, and you'll get the diagonalized matrix right there. So that's just sort of a clarification over there. Okay, and I think I got a bit confused. So I just wanted to explain over here that A is x inverse dx, so D becomes x A x inverse. So by just pre-multiplying and post-multiplying by x inverse and x, you'll find that if A is this, then D is that. Okay, oh wait, I messed this up again. Oops. I knew. Okay, so D is x inverse AX, and A is XD. There you go. D is, all right, I got this right this time. Sorry about that. So D is defined as x inverse AX, as X is the matrix. X is the matrix with the eigenvectors as the column matrices. A is defined this way, so therefore we get the fact that A to the M is x, D to the M, x inverse, which is what we use for the computation of A to the M. Okay, so everybody okay with this? And I keep forgetting the order, and I hope this is clear though. Any questions about this? Okay. Hi Mohammed. I didn't see. Okay. So let's move on to the actual topic for today, which is stochastic matrices. And stochastic matrices arise primarily in the study of queuing theory. Now, we're not going to do queuing theory, but I'll give you a good, hopefully an intuitive understanding of the meaning of a stochastic process. And that will motivate the use of a stochastic matrix. But let me first start with the formal definition of a stochastic matrix. So stochastic matrix is, to be more precise, let's consider what's called a right stochastic matrix. And a right stochastic matrix has these following properties. One is that it is square. Second, it is non-negative. It is real, so no complex. And fourth, the sum of the Aij summed over the row entries is equal to 1, right? So if you take this matrix over here, let me just write down a small, I'm going to use the example over here. So there's 0.25, 0.5, 0.25, 0.1, 0.9, 0, 0, 0, 1. You'll find that this is a right stochastic matrix because all the rows sum up to 1. It's square, it's non-negative, it's real, so it satisfies the definition, so it's a right stochastic matrix. Okay. We have something called the left stochastic matrix. And it basically means that the columns sum up to 1. So sum over I, Aij equals to 1. So if the transpose of a right stochastic matrix is a left stochastic matrix, okay? And in almost all cases when we say stochastic matrix, we automatically assume it's a right stochastic matrix. And a right stochastic matrix is also given another name, it's called a Markov matrix. We'll explain that in just a minute. Okay, that's just another name for it. Okay, so that's just definition, nothing particularly interesting. Let me now, I'm going to take a break from what's in the text, and I'm going to give you an example about what is a stochastic process, okay? So the textbook definition of a stochastic process is it's a set of probability distributions indexed by time or by a variable, okay? So it's a collection of distributions with some index associated with it. The definition is correct. It makes no sense. Okay, I mean, it doesn't make any sense at all. So I'm going to tell you how I think about stochastic processes, and in about 2 minutes you'll get it. So let's say there's a staircase, and on this staircase there's a person who's standing there. On the side of the staircase there is a clock, and every second it ticks. It moves 1 second, it ticks, like this, like the clock right there. Okay, and let's say that what happens is that the person goes one step with every clock tick. So one step, like that. Okay, so if I ask you the question, where are they after 4 clock ticks? You know the answer. They're going to be, the first step they go here, second they go here, third they go here, fourth they go there. So they're going to be, this were in stair K, they're going to be at stair K plus 4 after 4 clock ticks. So you know exactly where they're going to be. We call this a deterministic process because we can determine up front where this person is going to be, right? So it's pretty straightforward. Any questions about that? I mean, it's really... There's a chair right here. Okay. So now what I'm going to do is I'm going to allow this person to take a coin, okay, and flip the coin, and if it comes up heads, they'll go up. If it goes tails, they're going to go down. Okay, that's all they're going to do. So in the same clock tick, so when the clock ticks, the person takes a coin, flips it. If it comes up heads, goes up, otherwise goes down. So where is this person after 4 steps? The answer is you don't know. Well, you don't know deterministically where that person is, but you know probabilistically where that person is. Why is that? Well, let's just see. So let's say the person is step K at time. Let's say let me just draw it like this. This is K. I'm going to just write it like this for convenience. K plus 1, K minus 1. These are just the stairs, okay? So at time step 1, they were on step K with probability 1.0, right? After one flip, at time step 2, they're going to be at K minus 1 with probability 0.5 and K plus 1 with probability 0.5. I'm dangerously close to the edge, I realize. I'm going to, okay, that's good enough. Okay, at time step 3, what's going to happen? Let's see. So I need to kind of have this K minus 2 state over here. With probability 0.5 multiplied with 0.5, which is 0.25, it's going to be here, okay? And then there's 0 probability of being here. There's 0 probability of being there as well, and it's going to come back here at 0.25, okay? And this one is going to go up to K plus 2 with probability 0.25, okay? And there's no probability of being here, this plus 0.25, so actually it's going to be 0.5 of being in stair K, all right? So what are you seeing over here? That's a distribution. It's a distribution which is a discrete probability distribution which has 2 points on it, K minus 1, K plus 1. This is a distribution which has 3 points on it, okay, at K plus 2, K and K minus 2, all right? And what you'll see is that if you continue this process, what do we get? You get a distribution, a distribution, a distribution, and so on. And we get a set of distributions indexed by what? Time. And that exactly is a stochastic process. So a stochastic process is not one distribution, but a series of distributions where what we're doing is we're taking a distribution and we apply onto it some operation, we get another distribution. And the minute you think about this, you say, hey, wait a minute, this looks like a vector, and that's a vector, and we just learned that matrices are transformations. So maybe I can take a matrix and represent this transformation, and I can use this matrix to represent the process of going from one vector to another vector. Okay, so that's where matrix as transformation becomes a very beautiful insight. So what we do is this. We say, okay, let me take this matrix. In fact, let me take this matrix And what I'm going to do is that, okay, let me just call this matrix A. And what I want to do is I want to sort of figure out how to apply this matrix onto the probability vector. Okay, so let's say the probability vector of being in some set of discrete set of states is represented by, you know, P1 up to Pn. What am I calling it? Pn, yeah. So I have some set of probabilities of being in some kind of state, okay? Now, I haven't given any interpretation to these at all, okay? But I'm now going to attach an interpretation to this. And the interpretation I'm going to attach is that I'm going to associate each column with a state, okay? And I'm going to say that this is state 1, this is state 2, and this is state 3. And then this I'm going to interpret as a probability. So this probability 0.25, I'll interpret, and let me just draw these states as circles. That's the conventional representation. So I have 1, 2, 3, looks like a finite state machine. And I'm going to say that the probability of going from state 1 to state 1 is 0.25. And we draw that as a self loop with 0.25 on it. Then from state 1 to state 2, we get the probability 0.5. And then from state 1 to state 3, we got the probability 0.25, like so. So the fact that the row sums up to 1 is nothing more than the fact that at the end of the clock tick, when you're in the staircase, you've got to be somewhere. You've got to be on the same step or one of the other steps, okay? So the rows have to add up to 1. That's just the very obvious interpretation of these probabilities summing up to 1. Similarly, we say that we have 0.1, 0.90. So if you're in state 2, you're going to be going to state 1 with 0.1. You're going to stay in state 2 with 0.9. And there's 0 probability of going to 3, so I won't draw that. And then 3 has this interesting property that you stay in 3 with the probability 1. What does this mean? If you ever get to step number 3, you never leave. You get to 3, you never leave, okay? And that's called an absorbing state. You're absorbed into that state, and it's a black hole. You know, you go in there, oops, it's quicksand, you can't leave, okay? So you die there, because the probability of leaving is 0, okay? So you can call that the graveyard state if you want. You know, that's where you die, and you never leave that state. And so that's a finite state machine. So now we have this another beautiful similarity, which is that in computer science, we study finite state machines. You know, you think of Mealy machines and Moore machines. If you remember your undergrad computer science, we talked about those finite state machines. So there we just talk about states, and we talk about transitions of states depending typically on some event. You know, we read something from the input, we do something, go to another state. So that's we can represent complicated things like parsing of grammars, so context-free grammars as finite state machines, and we understand that. Here we have the same finite state machine being represented essentially as a matrix. And in this case, by associating these probabilities, we get a stochastic matrix from it. Okay? So what I've shown you is sort of 3 things. The first, we have a deterministic process, but by adding a probabilistic event at each step, we get a stochastic process, which is a series of distributions indexed with time. That's the first thing. The second thing is that because these distributions can be written as vectors, okay, these are, remember, discrete distributions, not continuous distributions. For continuous case, it's a different thing, but I won't go there. Because these are discrete distributions, I can represent them as a vector, and because it's a vector, I can view a matrix as a transformation. Now, I haven't showed you how the matrix works, and I'll show you in just a moment. But there is a very natural interpretation of this matrix as a finite state machine. Okay, there's one more point I want to add over here, and that's why it's called the Markov matrix. And I'm going to erase this for just a moment, and I'm going to explain something that's very important. It's called the Markov property, and it's named after the Russian mathematician Markov. And what it says is that when I get to state 2, for example, okay, I'm going to go to state 1 with probability 0.1 and stay in the state with probability 0.9. The fact that I'm making these decisions is independent of how I got there. Okay, so for example, let us say that 3 had the probability of 0.1 with 0.9 it got here. So let's see how many different ways we can get to state 2. We can get it from this way. That's one way. We can come in as a self loop, and we can come in from 3. Okay? But no matter how we got to state 2, we've completely forgotten the past history. Our egress probability of 0.1 and 0.9 are independent of the past history. Okay? Or another way of putting it is that there is enough information in that state so that all past history can be forgotten. Okay? And this is a very important assumption because it completely simplifies the analysis of this chain, of this what's called a Markov chain. This is another word for it, it's a Markov chain. And it's so simplifying that it's used everywhere, but there is a very important property to it, and I'll tell you what this means in a practical sense. It means that, let's say I'm walking like this and I'm at this position right here. At that moment I've forgotten that I'm coming in that direction. I may just as well go back. Okay? So if you're walking down a hallway and you have Markov property, at every instant you have some probability of just going back the way you came. Okay? You just completely forgotten where you came from. All right? You just, it's like every moment you've forgotten your past history. So it's a rather funny assumption, right? It's like history doesn't count. Okay? No matter what it is, at this moment in time, all that matters is where you are right now. So it's a very Buddhist interpretation of reality. Okay? Only the present moment matters. The past history doesn't matter. Future doesn't matter. All that matters is the present moment. So if you're a Buddhist, you believe in Markov property. Okay? Or at least you try to be a Markov person. Okay. Was Markov a Buddhist? I don't know. Probably not. He's probably an Orthodox Christian or something like that, but his theory is very Buddhist. Okay, to come back to this, the reason why I emphasize this is because many people assume Markov property without actually verifying that it's true or not. Okay, so a classic case is when you have modeling of mobility of vehicles in the city. Okay, so you have a vehicle in the city, so you can say, okay, that's some traffic intersection and some other traffic intersection. So I go from here to here with some probability, and I go from here to some probability, etc. And people publish papers like this. Okay, and they say it's Markov because you can analyze it this way. But it doesn't make sense. It's like saying I'm going down King Street, I see a light, suddenly I decide to turn around and go right back. Okay, that's not true. You never do that. If you're going in this direction, your past history tells you you're going to continue to go in this direction. So you have the past history over there. Okay, so these kinds of simplifications are often slid in the paper as an assumption. We assume it's Markov. Okay, and you say, well, it's not Markov. Reject. Okay. It's a nice way to get rid of papers. So I get a lot of papers to review, and I always find easy ways to reject them. So if anybody says it's Markov, the first thing, is it really Markov? No, it's not. Okay, reject it. Easy. So before you do the same thing and you assume it's Markov, make sure it makes sense. You can't just assume somebody's oops, sorry, I went back. Now if you're a professor, yeah, you probably forgot something in your office and you ran back. But most people don't do that. Okay, I'm going to do one more thing, then I'll stop, and which is that how do we actually use this matrix in computing some things? So I've showed you this, but we're almost there. So let's call this matrix A, and what I want to do is I want to use this matrix to compute these transition probabilities. So let's see, how do I want to do this? Okay. So let's say that I have some matrix which represents the probability of being in some particular state. Let's say I'm in probability of being state 1 at 0.9, 0.5, this is 0.4. These are probabilities of being in a particular state. So I'll see the state this way. So this is state 1, this is state 2, and this is state 3. And I'll call this vector P. The important thing to notice is that what is the new probability of being in state 1? It's a probability of being in state 1 and staying in that state. Yeah?
Just what you were saying earlier about no history.
Yeah.
I agree with the general concept, but with direction, you could extend the alphabet, like the number of states.
Yes.
Also include I'm going forward or I'm going backward, like which direction I'm generally going on right now.
Yes.
And then the probability would be different.
That's correct. So the observation is that by expanding the state size, you can certainly make it look Markov. What you do is you say it's not just the location, but it's also direction, okay, or direction it came from. And now I'm going to tell you the probability of where I'm going to and the direction I'm going from. What happens is you get a state explosion. Okay, you have a nice small, 10 states because it's 10 locations, but now I'm going to take direction that I'm coming from for each intersection. You have 4 directions plus it'll tell you where I'm going to, and you'll quickly find that you have this enormous number of states. So what you trade off to keep the Markov property is to have a very large number of states. Okay, and it's quite sparse actually. So there's the naive representation of Markov, which does not take into account the state explosion, is what you should reject. Okay, but you have to check the Markov property. I didn't say reject it because it's Markov. I said check the Markov property. So if you have direction in it and the Markov property is satisfied, that's good. But it's an easy property to check. Okay, let's go back over here. So let's see. Let's call this probability P1. This is P2. This is P3. I want to know what is the probability of being in state P1 after one transition, after one step. Okay. So I'm going to be in state P1. Okay. I'm going to be in state P1 if I'm in P1 already and I have some probability A11 of being in P1. It's a self loop, right? Because that's A11 over there. Plus, I'm going to be in P2 and there's a probability of A21. So I go from 2 to 1. Or I'm in P3 and I'm going to be in A31, right? So clearly, if I have a 3 by 3 matrix, that's the probability of being in P1. Either I'm there already and I stay there, or I'm 2 and I come there, or I'm 3 and I come there, right? That's clear? So how do I get that sum? If I look at it, this one is A11, this is this is A21, and this is A31, okay? So it's inconvenient, right? It's along the column, and I really want to have it along the row. Because if I have it along the row, then a simple matrix multiplication is going to give me that sum, right? So I say, oh, wait a minute. Let's take A transpose. If you take A transpose, we get this matrix. I'll just draw it over here. And so 0.25, 0.5, 0.25. And that was 0.9. 0.1, 0.91, and 0, 0, 1. And then I write the transition matrix over here, which was 0.1, 0.5, 0.4. And this is AT, and this is P. And this is going to give me, let's call that P, at step K is going to give me this matrix, which is P, K plus 1. And that's because of this over here. So if we take a right stochastic matrix, and its transpose, then simply multiplying the right stochastic matrix, the transpose of that matrix with the current probability at step K, let's call that Pk, right? That's a vector Pk, and that's going to be whatever Pk1, Pk2, Pk3. That is going to give me this K plus 1, which is just the multiplication of the transpose with Pk. You cannot multiply A with Pk. You have to multiply A transpose with Pk, otherwise this doesn't work out. Okay, so it's important that it's a transpose. Okay, so any questions about this? So you've all done this hopefully in the homework. Yeah.
Could we have just started with the left stochastic matrix?
Yes, if you had a left stochastic matrix, then you would multiply PA. Sorry, not PA. Okay, so if you represent A in the left stochastic matrix form, then you can just use AP. Is that right? I think AP or PA, I have to think. Okay, so basically, let me think about it. I think you can, but before giving you a definitive answer, I know that this works. Okay, and I'm not that smart. I can't think that fast on my feet. So if you say it's true, let's verify it. It's a very simple thing to verify. Okay, but certainly this works. Okay. Okay, let me just see if I have everything that I want to talk about, stochastic processes. So I just want to say over here that so I want to just say P I K plus 1 time step is equal to basically AT, or P K plus 1 is equal to AT PK. That's the equation that we want over here. So I wanted to just clarify something. So I explained that if A is a right stochastic matrix, then pk plus 1, the probability distribution, the discrete probability distribution at step k plus 1 is given by atpk, and it's clear that pk plus j is going to be given by at to the power j pk. So in other words, we can repeatedly apply the transpose of A to compute j steps. Okay, and so in the homework question, if we wanted to compute this one, so we're starting with the state. Let me just write the initial state. The initial state is probability 0.5 being in state 1, probably 0.5 being state 2, 0 being in state 3. And what we need to do is to apply the transition matrix, transpose the transition matrix twice. And that one would be 0.25, 0.25, 1, 0.1, 0.4, 0.5, and then 0.8, 0.1, 0.1. And if you compute this, you should get this matrix, which is 0.47625, 0.22375, 0.3. And really what you wanted was this number, 0.3. So if you write answers 0.3, that's a probability of being in state 3 after 2 steps. Okay, and that's basically all you needed. The rest is not quite necessary. So if any writes on 0.3, that's the answer. Okay. Any questions about this? Okay, so it's, yeah.
For the homework, do you want the full steps or just the last?
Just the last step. Yeah. I figured that if you got the right answer, either you cheated or you know what you're doing. If you cheated yourself. You didn't cheat me, right? Because later on in life, when you need to know how to compute stochastic matrix, say, oh man, I wish I hadn't cheated it because I'm going to fail this entry test to Google because I'm trying to do this. Google gave you this thing, and you say, I flunked this. I'm not going to get a job at Google because I cheated. It serves you right. I don't have to do anything. The universe will take care of it. So that's as I said, the karmic law of grading. I don't have to worry about it. Okay, so having said that, let's move on to looking at the eigenvalues of a stochastic matrix, and then I'll do the second homework after that. So having a stochastic matrix is nice, but it gets even more fun once we are able to compute the eigenvalues for stochastic matrix. So first I'm going to just give you some properties of the eigenvalues of a stochastic matrix, and then in the last bit I'll talk about the PageRank algorithm for Google, which in fact depends on the eigenvalues of the stochastic matrix. And so it's kind of a nice, really nice way of showing how linear algebra and stochastic matrices can be applied to make a very big company. Okay, it did actually start this way. Okay, so first, let me just write on the properties. Okay, so first property is that every right stochastic matrix A has an eigenvalue of 1. Okay, so I'm just going to show the proof here very simply. Basically what you're saying is that if A is a stochastic matrix, there exists some x such that Ax equals x. Okay, not ATX but Ax equals x. So how do we say that? Well, let x equals this vector 1 1 1 1 and so on. Okay, then Ax is going to be, let's just look at that. A is going to have this thing, this row, and this row equals 1. This summation equals 1. So when I multiply, when you multiply this with this column over here, okay, I'm basically going to get 1 because I'm just adding up the row. And I'm going to do that for each of those rows, right? And I'm going to get 1 1 1 1 1. So I get, okay, and that is x. So what this is doing is just adding it up to 1, right? I'm just adding up the rows, and I told you by definition the rows add up to 1. So it must be the case that for the eigenvector the eigenvector is given by 1, 1, 1, 1, 1, and so on, there is an eigenvalue of 1. Okay? And this is a point where you should be confused for just a moment. Okay? And the reason you should be confused is because I just told you that ATP equals P, and P is a probability distribution. A probability distribution is going to be a set of numbers that add up to 1. Right? But here I have an eigenvector which adds up to n, not 1. It's each value is 1. So what's going on? And the answer is that this is the eigenvector corresponding to A. The eigenvector corresponding to AT is not going to be 1, 1, 1, 1, 1. The eigenvector corresponding to AT, the transpose, will have elements which are going to be adding up to 1, okay, but not the eigenvector corresponding to A. Okay, so you'll be very careful what you're looking at. You're looking at the A, or you're looking at A transpose. Okay, so interestingly enough, the eigenvalues. Okay, so let me just stop there for a moment and just emphasize that what I've showed is that every right stochastic matrix A has an eigenvalue of 1. Okay, has one eigenvalue of 1. Okay, that eigenvector corresponding to eigenvalue is this eigenvector over here, and because of this simple math over here, I haven't said anything about the eigenvector corresponding to A transpose at this point. Okay, so any questions about this? Yeah.
Yeah, sorry, even the eigenvector corresponding to A could be add up to 1, right? You can divide them by n.
You can divide them by n, well, but then you, but it won't be, well, let me put it like this. If you want to do that, then lambda would be equal to 1 over n, yes, if you were to do it that way.
Yeah.
But I'm just showing you that in this particular case, I don't have to do it.
All right.
Okay, but the important point is the eigenvector corresponding to A and A transpose are not the same, even though they have the same eigenvalue. So I can't just compute the eigenvector corresponding to A and say this is the same eigenvector for A transpose. Okay. Okay, let's just keep this. That's what I want to say here. All right. But yes, you could have the eigenvalue of 1 over n, but that won't be an eigenvalue of 1. Okay, I want the eigenvalue 1, not 1 over n. Okay. The second thing is that the eigenvalues, this is a eigenvalues of A and A transpose are the same. This is this fact for any matrix, that the eigenvalues of a matrix and its transpose are the same. So this means that A transpose has an eigenvalue of 1. Okay? Just because of this fact over here. All right, so now we established that both A, stochastic matrix A, and its transpose both have an eigenvalue of 1. I've showed you what the eigenvector for A is. I haven't showed you what the eigenvector for A transpose is, and we'll come to that in just a moment. Okay? Any questions about this so far? Okay, so let me write down a few more properties. So we'll go to 4. The second property is that every eigenvalue of A has a magnitude less than or equal to 1. Okay, so what I'm saying is that not only do I have a magnitude, one eigenvalue of 1, at least one eigenvalue of 1, because it could be repeated. Moreover, every eigenvalue has to be smaller than or equal to 1. And how do I show this? The proof is based on the circle theorem. So let's just look at this. This is a complex plane. So I have the real axis, and I have the imaginary axis over here. And I'm going to choose. So let's just look at what the matrix looks like. The matrix is going to have some things, and I'm going to pick the diagonal element. So let's just take this AJJ element. Let's say it has a value x. Okay, it has a value x. Because the row sums up to 1,